Hello everybody, I'm Xinya Zhang, a PhD student from the University of Texas at Austin. My research interests are physical simulation, graphics, and motion planning. Today, I'm going to present our latest work, the safe-space tunnel discovery for puzzle path planning, in collaboration with McGill University. Our motivation comes from a classical problem, motion planning. Motion planning can be found everywhere in robotics, from robot grasping to assembly of industrial products, and to autonomous driving. There are a lot of existing works in this area, but most of them still struggle with a simple type of problem, the disentanglement puzzles. In our paper, we are going to solve these disentanglement puzzles. I think everyone else has once played or seen such kind of puzzles. They are designed to be hard for humans to solve. And in our work, we are going to present a computational way to solve these problems. Our solution is a three-stage pipeline. First, we decay features from each piece of the puzzle. Then, we generate key configurations according to the features. Afterwards, we will use these key configurations in our motion planning algorithm to find the solution path. But before we start, we need a little bit of background. Let's consider this 2D problem. We have a 2D workspace and a workspace obstacle shown as teal on the right-hand side, as well as a moving piece shown as red. To describe the configuration of the red piece, we need three numbers, x, y, and theta. X, y for translation, and theta for rotation. Therefore, we can introduce a concept called configuration space, or C-space, which is the set of all configurations. For this case, the C-space is 3D. With the introduction of configuration space, we can translate any movement in workspace into a particle's movement in configuration space. Therefore, we can formally define the motion planning problem into finding a trajectory in configuration space from initial state to goal state without collisions. With this formal definition, we can discuss a classical motion planning algorithm, the rapidly exploring random trees, or RRT. The overall goal RRT is to extend the tree inside the configuration space. In each iteration, RRT will first sample Q in C space and try to find the nearest vertex V in existing tree. Thus, it can connect V to Q. If the connection failed, no edges or new vertices will be added to the tree. The algorithm will terminate if it reaches the goal or timeout. The right-hand side animation shows how an RRT tree expands in the configuration space without obstacles. There are quite a few challenges in RRT algorithm. The first challenge is narrow tunnel problem. Consider the previous configuration space. It has two towers connected by two narrow tunnels. If we are not lucky enough to have a sample inside the narrow tunnel, we can only extend our RRT tree on the right tower and cannot go into the left tower. Therefore, we cannot solve the problem. The second challenge comes from a counterintuitive phenomenon. We probably would think we will have a better chance to solve the problem by running RRT for more iterations and building up larger trees in the configuration space. But this is not always the case. We call this phenomenon sample interference, which can be demonstrated in the following example. Consider we want to enter a chamber. Initially, as long as we can sample inside the blue region, we can enter the chamber because the nearest vertex is the root of the tree. However, after a few iterations, we have a larger tree. If we still have a sample inside the blue region, the nearest vertex becomes the green vertex above, and that's blocked by the obstacles. We can only enter the chamber by sampling inside a much smaller yellow area. Formally, this problem can be described as the Voronoi area belongs to the right vertex becomes smaller. The third challenge is the exponential decay of the probability to find a solution. Let's use the Hanayama duet puzzle as the real example. Consider we can solve the single grid version with the probability of p. The theoretical probability to solve the full version of the puzzle is p to the 19 because there are 19 narrow tunnels on the solution path. In reality, the probabilities to solve the full version is much worse than p to the 19 because of sample interference. Our motion planning algorithm usually cannot maintain the probability of going through another narrow tunnel. Motivated by existing works, we use feature detection and configuration generation algorithm to locate narrow tunnels, and then use forest-based motion planning algorithm to address sample interference and exponential decay of chance to solve simultaneously. In the first stage of this pipeline, we propose 3 different feature detection algorithms. The first algorithm is Euclidean to geodesic ratio. The motivation of a Euclidean to geodesic ratio is to detect a gap in the workspace geometry. A workspace gap can be detected by a pair of surface points that's close in Euclidean distance, right? Well, if we really use this algorithm, we will have a lot of false positives. Thus, we introduce another criterion, which is the geodesic distance. We then use the Euclidean to geodesic ratio to detect the gaps in the workspace geometry reliably. Our feature detection algorithm starts from a uniformly sampled mesh vertex U, and then finding another initial vertex V from the local minimal of the Euclidean to geodesic ratio field by fixing U. The yellow sphere here is the midpoint between U and V. Starting from the initial UV, we use gradient descent to minimize the Euclidean to geodesic ratio. And the final output is the Euclidean to geodesic ratios feature. Since the U is uniformly sampled over the surface, this is a Monte Carlo algorithm. We then run this algorithm multiple times in order to find all possible gaps. We encourage you to see our paper for the extra details we not talk about here. The second feature detection algorithm is medial access notch. The medial access notch is based on this motivation. We would like to detect the notches on the pieces because this part is likely to formulate a narrow tunnel in the configuration space. Let's look at 2D analog to see how we find the notches in the geometry. To do this, we first compute the medial axis in the geometry, and then we cluster the vertices of the medial axis according to the distance to the boundary. Therefore, the local minimal groups are the notches detected by us. Here are real examples of notches detected by our algorithm. Our algorithm is able to detect notches on the backside, but unfortunately, there are a few false positives there, but they can be discarded later easily. The last feature detection algorithm is the neural network. The motivation of a neural network is quite simple. We would like to learn from the easier puzzle to solve the harder puzzle. The framework of our algorithm is we first train a neural network on easy puzzles to identify the region of interest. We then apply this network to multiple views of a harder puzzle. Thus, we can build a texture map according to the output from different views. To generate a training data, we use a 3-step algorithm. The first step is to find a solution with a classical planar. Secondly, we will detect narrow tunnel configurations on the path. At last, for each narrow tunnel configuration on the path, we apply a set of random transformations, collect the collisions, and then build a texture map according to collisions. This is a real example of the ground truth generated by our algorithm. The left-hand side shows the solution path, the right-hand side shows the accumulated result from the collisions. To train our network, we randomly choose a view of the puzzle and then render the depth, luminance and normal along with the ground truth into images. We then use this data to train our network. The missing blocks here are the result from data augmentation. We encourage you to see our paper for further details. The inference is a similar process. We randomly choose the value of the harder puzzle, render depth, luminance, and normal, and send those data to the neural network. However, the output is blocky and noisy and cannot be used directly. The key to the success is to summing among thousands of values. Here are a few prediction results, which are depth maps synthesized from many values. We can say one advantage of neural network approach is we do not need a new algorithm to detect new type of features. We just need a new training puzzle. With all these features detected by our feature detection algorithm from each piece of the puzzle, we can then proceed to the next step, key configuration generation. But before we start, we need to recall different types of features from different algorithms. The Euclidean to geodesic ratio, or media access notch feature, is a pair of surface points, shown as the yellow cones in the video. The neural network feature is slightly different. It's a surface point with its surface normal, because the output of the neural network is actually a density map. We have to sample on the density map to get a neural network feature. The first type of key configuration is generated from a pair of Euclidean to geodesic ratio features. We first align the midpoint of the two features, and then keep the features orthogonal. This leaves us 2 degrees of freedom. We can then apply angle sweep algorithm to enumerate all the rotations. The dots in this image shows collision-free configurations from the enumeration of the rotations. The circles marked the 4 key configurations in the null tunnel, and the 2 large isos are collision-free configurations, but they are not in a tunnel. To reduce the total number of key configurations in the output, we cluster and merge key configurations. The second type of key configuration is generated by matching a Euclidean to geodesic ratio feature to a media access notch feature, or more intuitively, a gap against a notch. We align the gap and the notch, thus leave us 1 degree of freedom. We can apply 1D angle sweep to enumerate all the rotations, get all the collision-free configuration, and at last, cluster and merge key configurations. The third type of key configuration is generated from a pair of neural network features. From the video, you could say it's quite similar to key configuration generation from Euclidean geodesic ratio against the media access notch features. The crucial difference comes from the types of features we are using. Instead of aligning line segments from surface points, like we did before, to align neural network features, we have to align surface points along with their surface normals. With all the key configuration generation algorithms, we are able to generate a field to thousands of key configurations. To utilize those key configurations, we designed a forest-based motion planning algorithm to find a solution effectively. We first seed those key configurations as routes along with the start and go configuration into the configuration space. Then we use RDT to bloom those routes into a forest. Third, for each vertex in the forest, we try to connect it with k nearest vertices. However, this is not enough for good performance. We encourage you to see the paper for additional optimizations we used. Last, we use a hierarchical breadth-first search for good performance in larger forests. We tested our pipeline against a variety set of puzzles. These are the puzzles we solved. We have the wire puzzles from alpha family to the cloud, as well as a set of Hanayama puzzles. Here is the solution video to our puzzles. Our Euclidean to geodesic ratio feature detection works best for those wire puzzles because it can detect the gap reliably. The media access notch feature detection makes no sense for the wire puzzles, but we still include them in our tests to show the robustness of our motion planning algorithm. The neural network algorithm works for every type of puzzle. However, for each specific puzzle, it's worse than the right geometric feature detection algorithm. The Enigma puzzle is the first puzzle that requires a median access notch to solve. And the duet puzzle is the design motivation of the median access notch, and clearly this feature detection algorithm works for this puzzle very well. The Mobius puzzle is a little bit weird because every configuration in the solution path is actually Newtonian configuration. The ABC puzzle, along with the key puzzle in the next, are the two most difficult puzzles, which require thousands of key configurations to solve. These puzzles, along with the key puzzle, show the robustness and scalability of our motion planning algorithm. We compare our algorithm against a few baseline planners and the equal effort criterion. To estimate the success rate, we run 10 trials for our solution and 100 trials for baseline solutions for better accuracy. Baseline planners are the standard planners coming from the Open Motion Planning library. You could say our solution can solve those puzzles in very high chance of success rate, while the baseline planner usually suffers from low chance to success, or running out of time, or running out of memory. We have more in-depth evaluations in our paper, like the strength of each strategy, detailed statistics numbers, and the implementation details. We encourage you to see our paper if you are interested in those details. We care about the reproducibility of our work. We have a dedicated website which includes the links to our paper, our code, and as well as an interactive 3D visualizer to our solutions. We published our code on the GitHub. A Docker file is also included so everyone can build our project without too much trouble. The puzzle geometry used in our paper is also published on the internet. In conclusion, we proposed a versatile approach to motion planning problems. Each component in our pipeline reveals new research directions or new applications. For example, we can have new drop-in geometric features as our feature detection algorithm. Our neural network pipeline makes pattern recognition in configuration space possible. And our force-based motion planning may have new source of key configuration inputs. For example, the user input. Last, those insanely difficult motion planning problems are solved. We look forward to your questions.